So here's one Mobius strip, right? And maybe, so here's, let's say this guy is another Mobius strip. Let me use this different arrow to indicate these. Okay, and now remember that these guys had some boundary edges, right? So this was the boundary edge, and this is another boundary edge. Okay, right. So okay, so we have various yeah. So let's see. So we have some answers. So what happens diagrammatically? Let me try to do this here. So yeah, so I see the correct answer already. Some of you might have already sort of seen something like this, or you've guessed correctly. So let's try to see what happens when you try to do it in diagram. So now this guy, I'll think of as sort of gluing it to, let's say this edge. I'm going to glue to this edge, right? I'm going to take. Let me try to take this guy here. So, oops, I'm going to take this guy and I'm going to bring it here. Okay, so bring it here, and then I'm going to, so that's one gluing, and the same edge continues, right? So then the continued guy, let me just, oops. So let me, so let's say this, it goes here, then it continues there, right? So this was the edge this way. So now, let's see, so sorry, so let me try to do it this way, right? So if I start here and go there, then I kind of continue there this way. All right, but now when I do this over here, so let's see what happens. So then this goes this way and this goes this way, right? So then you go this way, right? So this is the diagram of what these two. So now you can sort of put these two together because they're glued, and so I can just draw it glued. They're right next to each other. So when you draw them glued, oops, let me try to draw a better square. So when you glue them, you get, so now you get, so this was this double arrow guy, right? I've glued it up. So I'm going to erase it completely, but the other things I keep. So it's like this, and this, and this arrow and this arrow. Okay, so what is happening is, just like, remember the torus, so the torus was where I glued opposite sides, right? So if I just had this and this, and this, that was a torus. But this time, if you see what is happening, so if you look at the left edge and the right edge, these are exactly sort of opposite directions. Okay, so you're gluing by this half twist, if you like. So this is, whatever the surface is that I get is equal to, if you take a square and glue top and bottom as you would on a torus. Okay, this you glue it directly across, but the left and right sides you can glue with this this half twist, the arrow going the other way. Okay, and this surface that you get is called a Klein bottle. Okay, so this is a Klein bottle. Okay, and why is it not a sphere, for instance? Somebody guessed it's a sphere. Well, it has as a Mobius strip sitting inside it. If you think about it carefully, so if you look at this portion in between the dotted lines, okay, that's a Mobius strip sitting there, because because this left edge and the right edge, they differ by this half twist. Okay, so it contains a Mobius strip. So that's something that's different from a sphere. Okay, in fact, in topology, we say it's a non-orientable surface. Okay, so it's so it contains a Mobius strip. So let me just write it down. So it contains an embedded Mobius strip. So already this tells you it's different from a sphere, right? Because remember, you can embed K5 on a Mobius strip. Okay, so you can put K5 in this picture here, but you couldn't do that on a sphere, right? So that tells you it's different from a sphere. So let me just mention that again. It can so one can embed K5. Okay, and this Klein Bottle. So let me actually show you an animation which shows this construction. So remember that a torus, when you glue it, with opposite sides like this and like this, straight, both in the same direction, then the first gluing gives you a cylinder, right? It gives you some cylinder. Maybe this is behind you, behind this thing, right? So this is what happens when you glue the top side to the bottom side, and then when you glue this side to this side to make the arrows match, right? So when you make the arrows match and glue this side to this side, you get a torus, right? But now for a Klein bottle, so this was for a torus. For a Klein bottle, the arrows, it's sort of pointing in opposite directions to the case of a torus. So this arrow would be this way and this arrow would be this way. And now when you try to glue, okay, to make the arrows match, you find that you can't quite do it remaining, remaining embedded in R3. Okay, so you have to kind of intersect yourself. So here's an animation of that happening. So here's this is taking this two sides, making the arrows match. You have to kind of pass through the surface and glue up. Okay, and that gives you a Klein bottle. Okay, and it's just like the Mobius strip was one-sided surface. This is going to be Klein bottle is the shape with so where the inside it's and outside there is no are connected. Okay, so it's sort of it doesn't, just like a sphere, it kind of has an inside and you have an outside. It separates R3 into two pieces. So a Klein bottle doesn't do that. Okay, so once again, so here you have this cylinder as usual, but now to make the arrows match, you have to kind of pass through it. And so this is the typical view of what a Klein bottle is, right? Okay, so right, so one can compute the Euler number of the Klein bottle, and there is a graph sitting there already, because you can have, if let's say these edges are your edges of the graph, and the vertices are so this vertex is the same as this vertex because this is the bottom side of this arrow pointing up, and then this guy is the same as this guy. But then, so there's only one vertex. All these vertices are identified, right? Because by these identifications. So there's one vertex, and there are two edges. So let me draw sort of color the two edges we're doing. This is one edge. This side is identified with this side, and this is another edge. This left side is identified with that. So that's your graph, and the region that you see here is only this interior of the square, right? So that's the region. So if you compute the Euler number, it's the number of vertices, which is 1, minus the number of edges, which is 2, plus the number of regions. So that's 0. So it's the same as that of a torus, right? But it is not a torus, okay? Why is it not a torus? Well, because it has a Mobius strip inside it, okay? So this is not a torus, since it it is not orientable. Okay, and I'll send another video link on what this orientability means, but it's not orientable for you. It just means that it's not orientable means it contains an embedded Mobius strip. So, which we already saw, it contains a Mobius strip. For a torus, it doesn't. Okay, so contains a Mobius strip. In fact, there's another way that it's different from torus. It turns out that so another difference with the torus in terms of some of the things we were seeing is that so a K7 cannot be embedded on in a Klein bottle, but it can be embedded on a torus, it turns out. Okay, so K8 cannot, but K7 can still be. So you probably have done K5 and K6. K7 is more complicated, a lot more edges, but it can still be put in embedded in a torus, but it cannot be embedded in a Klein bottle, it turns out. Okay, and let me just sort of, I guess I have a few more minutes.
So how did you get two edges?
Sorry?
Two edges.
Two edges because the ones that the arrow, the green edges with the same arrow are actually glued up when you do this, when you make the surface, right? So then they become one edge. Yeah. So I have these two pairs, right? So those two pairs, after gluing up, they become a single edge on the surface, right? Each of the pairs. So you have two edges.
It should be one, right, then? Because all are going to be connected, right?
No, so we have glued the top and the bottom, so that becomes one edge, and the left and the right, that becomes another edge, right? So they're not all glued up, right? So they're glued in pairs. Okay. Right. So by the way, so let me sort of ask another question. So what other surfaces can you get from gluing sides of a square? Okay. So here's another way, right? So this is, so if you have this, so I can glue this pair of edges, and I can glue, let's say, let me sort of not glue the opposite pairs. So this time, let me glue this pair, and maybe I'll glue this side to, sort of this side, and this side, and this side, and this side. So anyone, can you guess what surface you get? So by the way, by a surface, I mean that something that is locally, is topologically equivalent to a flat, sort of Euclidean plane, right? So locally, if you're an ant, right, if you're a tiny ant on any surface, locally your world will look, flat to you, right? So for a long time, human beings thought we were sort of, we were living on a flat piece, flat Earth, right? I mean, but it turns out it's actually a sphere. It's a different surface. Right, so topologically, you could be on a torus, you could be on a sphere, etc., etc. But locally, it always looks the same. So for this, can anyone guess what surface do you get after doing these gluings? If you want, you can imagine, doing these gluings. Just have a flexible enough piece of paper and then doing these gluings. Yeah, two cones with their base, etc. Somebody said sphere. Yeah, that's right. You do get a sphere. How do you see that? Well, if you do one of the gluings, right? Suppose I glue these the bold arrow. So then what you get is something that kind of might look like this. If you glue these sides, right? So then. Actually, so it's sort of harder to draw this, but this is supposed to indicate some kind of, suppose I glue, these two sides up, right? Imagine sewing them up, right? You take a sort of, imagine it's a piece of cloth, and then you kind of sew these two things together, right? So then you get something like this, and then when you sew these two together, then you will get, so you get this and this, and it's sort of you've sewn up a pillowcase, right, or some kind of, yeah. So that's topologically equivalent to a sphere. you.